Today, I am really delighted to welcome longtime colleague and a friend of the Hubble Space Telescope, distinguished member of our EC Science Committee, Mike Wong, who is an expert in atmospheres of planets in the solar system, researcher at the University of California, Berkeley, at University of Michigan. Today, we have quite a treat for you all, because Mike will speak about the 10 years achievement of the OPAL program. And I was just chatting with him a few minutes ago that I remember when this program was accepted as a very important treasury program with the Hubble Space Telescope in 2014, with this ambitious goal of studying the atmosphere of the outer planets, Jupiter, Uranus, and then Saturn was added later, if I remember correctly, because of the Cassini work. So this program celebrates now 10 years, and Mike will tell us about all the beautiful results that have been accomplished in this past 10 years. So Mike, I will give you the floor.
So I'm talking about the OPAL program today, and OPAL is an acronym that's been used by a lot of different projects. In this particular case, it stands for the Outer Planets Atmosphere Legacy Program. So OPAL started, as Antonella said, in 2014 with Uranus. Then in 2015, we got our first Jupiter and Neptune observations, and then Saturn in 2018. So we've really been getting more than 10 years of data so far. So the goals of the OPAL program are to explore science themes related to the long-term evolution of planetary atmospheres, including their circulation, atmospheric circulation and dynamics, and the chemistry that makes up their clouds. So the types of observations we get are visits to all 4 giant planets every year. And each time we visit the planet, we get a pair of global maps. And as the planet rotates twice, we can see features have moved here and there, and we can measure winds based on the displacement of individual features. The observations are all imaging data in filters that span the near ultraviolet to the near infrared, and this gives us the information we want on the cloud heights and color information that tells us about composition. So we do everything for this program, from programming the observations to processing the data. The raw data are immediately available on the Hubble archive, and then we take those raw data and convert them into cylindrical maps. And the cylindrical maps then are hosted on a special high-level science product page where people can download them either in scientific fits format or in graphic formats to use for any application they want. And here is the link to the archive page. And you can also just Google it, Google HST OPAL, and that should take you to this page. Although I don't know if that happens because it's in my browser history or if that's just like the first hit usually. So if Antonella was in the room, then she probably recalls this chart. So around 2014, when we proposed this, there was an issue with the giant planet observations, which is that for each of these planets, there were times shown as white boxes here when there were 0 observations of the planet that year. And so this could cause us to miss transient phenomenon and not have a good sampling of long-term changes. In fact, we did a study specifically for Neptune, and this chart shows, as a function of time, what is the chance that a dark spot that, if it were present on Neptune, would have been missed by Hubble observations. So depending on whether you would recognize it in a single frame or if you needed 3 detections in order to confirm that it wasn't noise, the probability varied. But there were several years where either way, Neptune just hadn't been observed and a dark spot could have been missed. And this is based on what we know, that they can last for 2 to 6 years. Now with OPAL, you can see its Neptune observations there starting in late 2015. That probability has dropped to 0. So if there's a dark spot on Neptune, we will discover it with HST. And in fact, we have discovered 2 of them with OPAL. So now the chart is much improved, and we have a new color here, purple, which is the type of observations we get from OPAL, which are better than most of the previous observations in the archive. So the pair of global maps really allows us to do a broader range of science. So the science with OPAL really started as soon as we got the first Uranus observations. This is me and Amy Simon presenting it at the LPSC meeting. And Amy Simon is the PI of the program. I'm the co-I. And we have a third co-I, Glenn Orton, shown in this picture from 2018, where all 3 of us finally ended up at a conference together. This is the COSPAR meeting in Pasadena. Finally, in 2024, Amy Simon was recognized with the Alexander Award for Mid-Career Scientists from the AAS-DPS Society. So that citation partly was due to her work with OPAL program. So OPAL, this is sort of my main bragging slide here. OPAL has really given us a lot of chances for early career scientists to contribute. So the table shows undergraduate scientists, graduate students, and postdocs. These are the ones who have led or have a paper in progress that they're leading based on OPAL data. And this ranges from papers that are entirely based on OPAL data to papers where OPAL data are compared with another data set, or OPAL provides context for modeling or observations of giant planet atmospheres. So quite a lot of early career involvement here, and there's also a table of the advisors. And one of the things that I'm really happy about is that many of these early career researchers, many of these advisors are not part of the OPAL team officially. It's not me, Amy Simon, or Glenn Orton. We have many other advisors across the world who have mentored early career researchers using OPAL data. Now, the table in the lower left there gives some statistics, and we can see here, based on the number of orbits, the OPAL program is the largest solar system program that's ever been conducted with the Hubble Space Telescope. 476 orbits. It's actually more than that. This was last updated in August of this year, but we now have more observations of Saturn. The OPAL program has resulted in about 70 publications to date. There's more in the pipeline, but that's the current number of published papers that are part of the Space Telescope Archive database. And in the last column here is kind of an efficiency metric. It's the orbits per publication. So out of every publication that comes from the program, how many Hubble orbits on average were required for that publication? So we have a metric of 6.8 here, and the only program with a better metric is John Clark's program from cycle 15, which is 2.4 orbits per publication. And that program was based on studies of the aurorae of Jupiter and Saturn. So again, it was a time domain program, but with a different focus than the OPAL program. Okay, so now let's move to the science highlights, and I will try to get through as much of this as possible. My goal is to spend about 45 minutes showing slides, and then we can take questions at the end. So the first one here is convective storms, and the background image is a global map of Jupiter, so you can see familiar features like the Great Red Spot and Oval BA next to it in the southern hemisphere. In the northern hemisphere, you may notice a bright white clump of clouds with a little stream behind it looking like a comet. That is a convective storm, and you can see it also in these images from the OPAL program here. This came out, this beautiful color processing was done by the Public Outreach Office at Space Telescope Science Institute, where they use different filter combinations. And it came out, I think, around July 4th, which is why we went with the red, white, and blue color scheme on the right. But this is showing us a major convective storm in the northern hemisphere. And storms on the giant planets come in different sizes. So the one we just saw was a large or superstorm size. There's also medium storms and minor, very small storms. So one of the things we've been studying lately with OPAL is actually this weird intermediate case, which I've been calling a stealth superstorm. So let's focus on the upper right. I don't know if I can do my laser pointer. No, I won't be able to figure that out. I don't know. But you can see my cursor here in any case.
Yeah, we can see your cursor well.
Okay, yeah, so in the upper right, we have a series of 4 maps. Now, this isn't showing the whole planet. This is showing mainly the north equatorial belt, a dark region of Jupiter. So it's 2019 to 2022 going upwards. And OPAL charted some changes in this belt. So the normal state of the belt is it's dark. It has a few small, I would really call these small convective storms. They're indicated by pink triangles here. 2020, again, small storms. The NEB is a normal wide belt. And in 2020, you can see that superstorm erupting here. These are processed with a different color scheme. 2021 was a really unique condition, and a lot of people paid attention to this, particularly the amateur astronomers. The NEB, which stands for North Equatorial Belt, had narrowed to a really, really skinny dark belt around the planet. So normally it's much broader. In 2020 and 2021, it was very narrow. And then finally in 2022, it had resumed its normal appearance, more or less, with small convective storms. But one thing you notice in 2021 here is there's no small convective storms in the NEB anywhere around the whole planet. And this chart in panel A here kind of shows a timeline of these small convective storms. And you can see that the convection shut off in this weird anomalous state in 2021. And then it started at a particular active longitude, I'm calling it. And then convective activity began to expand around that active longitude until, again, it was found at all longitudes of the planet. So this is showing some characteristics of the superstorms, but when you look at the individual storms, they are not that dramatic. They're much smaller. So yeah, the stealth superstorm, an analysis, well, this was discussed in a paper with Amy Simon and me last year, and there's a paper in press about, or under review, about the lightning activity as measured by Juno associated with these stealth superstorms. So what are we talking about when we consider convection in giant planet atmospheres? Well, the giant planets have a different cloud structure from the Earth. On the Earth, we only have water clouds, but on the giant planets, water clouds are perhaps the most abundant cloud layer. Here we're looking at Jupiter versus Neptune, but there are other exotic ice clouds, including ammonium hydrosulfide, ammonia clouds, methane clouds on Neptune, and H2S clouds on Neptune and Uranus. So among these different cloud layers, let's see, at the upper right here, we show results from a numerical simulation of how convection works in giant planet atmospheres. And the different colors are the different cloud types. So red is the water cloud, blue is the ammonia cloud at the top of the atmosphere. And in this timeline, you can see there's periods of time where there's a lot of cloud material there. That's a convective active time, and then there's quiescent times where there was less convective activity. So let's do an animation from this paper by Sugiyama et al. in Japan. And you can see in this simulation, it's a two-dimensional simulation. There's an active period. You can see an outbreak of clouds. And when this happens, it affects many properties of the atmosphere. It affects the thermal state. It affects the composition of the atmosphere. It dries out the upper layers. And then gradually there's mixing of material upwards until the upper atmosphere is moist again, and you can have another convective outbreak. So this type of episodic convection is something that we think is common among all the giant planets. Perhaps in the details are influenced by how much water is present in the planet's atmosphere. And it's also something that should be highly relevant to exoplanets. So here we have a case where our observations of Jupiter, Saturn, Uranus, and Neptune, much closer to us, can give us detail that helps us understand what we're seeing in the unresolved or partially resolved atmospheres of planets around other stars. So here are some images of Uranus and Neptune, and this is a mix of Hubble spacecraft and ground-based imaging sources. But this is kind of just showing that one of the questions that we're facing when we look at these more remote planets is what are the clouds telling us? It's clear that not all of the clouds are these convective plumes like the ones we can watch evolve on Jupiter and Saturn, but some of them may be. So this is kind of an active area of investigation, trying to figure out based on the types of clouds we see and their time variability, can we tell whether they're convective in origin or something else? So let's talk about the zonal winds. All of these giant planets have these powerful, very fast jets of east-west zonal winds. They're maybe similar to the jet stream that we're familiar with on Earth, but the Earth's jet stream is meandering in latitude. And in these giant planets with their very strong rotation and Coriolis force, the jet streams are constrained to flow east and west. So on Jupiter, the Hubble data have been very effective at measuring the speeds of these jets and measuring some subtle changes that we can detect with the high precision from Hubble. On Saturn, again, we can measure these zonal jets, and Uranus and Neptune, it's really the ground-based data that give us better information on the zonal wind flow. We have measured speeds of discrete features on these ice giant planets, but the zonal jets are not really characterized by the OPAL data. Now for Jupiter, we talked about convective storms before. Now we're talking about these zonal jets or zonal winds. There's actually an interaction that has been known before OPAL, but this really gives us a denser sampling of the time variability and allows us to see this interaction. So basically what's happening here, we're looking at a timeline of the wind speed of Jupiter's fastest eastward jet. And that jet increases in speed over time. And then when one of these superstorm convective outbreaks occurs, the jet speed drops by tens of meters per second. And then the speed will gradually build up again until there's another outbreak, another superstorm, and the jet speed drops again. So this has been studied with OPAL data, and actually, if you look really closely at the dots, some of those dots are closer in time, and that is thanks to some programs that were designed to, special programs to cover the Juno mission, which arrived in 2016. So this jet speed variation was known to some extent before OPAL, but the observations, including OPAL, showed that even some of these medium class storms, like this one in the southern hemisphere, were able to cause changes in the wind speed. And panel B here shows kind of that uncertainty envelope, and some of these changes are statistically significant. They're poking out beyond that red band. So this slide is kind of showing us a number of things. It's showing the high precision of Hubble measuring zonal winds, showing a new interaction between a different type of storm and the zonal wind field. And it's also showing us how different observatories work together. So in the upper right here, we can see some of these periodic storm plumes observed in the infrared with the IRTF telescope in Hawaii, maps from Hubble in the middle, and at the bottom, maps from the ALMA telescope in Chile, showing anomalies in the ammonia gas composition associated with this storm. So you can see how multi-wavelength observations from different observatories pair very well together. If you were just to look at the ALMA data, you wouldn't see necessarily the fine-scale cloud structure and the colors that Hubble provides through the OPAL program and other programs. Another synergy between two facilities is shown here, where we compare James Webb data with the Hubble data. And so the equatorial region of Jupiter, the wind speed is shown in white for Hubble observations, and it's known to have this double peak structure. But when we looked at James Webb data, we saw for the first time that there's a very narrow band right at the equator that's moving much faster than the surrounding winds. So that's something that was a new James Webb discovery. But because James Webb is looking at higher altitudes in the atmosphere compared to lower altitudes from Hubble, we can actually see that the wind shear has a different sense in this narrow equatorial jet compared to the off-equatorial jets that we had observed before with Hubble. So it's a great example of two observatories working together to provide more detailed information on the giant planet atmospheres. So I've done a lot of work with vortices. Here is an example of two dark spots on Neptune. In the upper left, we see the first OPAL observations of Neptune detecting a dark spot in 2015. And with OPAL, we were able to watch that dark spot fade away over time. And it seemed to have some little companion clouds that persisted as the dark spot faded away. So we got to watch sort of the dissipation phase of this dark spot, but because OPAL started in 2015, after a long spell of no Neptune observations with Hubble, we have no idea how that dark spot originated. In contrast, we saw a new one emerge in 2018, and the Space Telescope Outreach Office put together a nice animation here. And this shows an animation of the planet rotating, and you can see the new dark spot. And something new that we saw with this particular dark spot is that it had some small companion features, these secondary dark spots. So I don't know if they'll repeat. Yeah, I don't think they repeat the labeling. So let me just go back to this label here. You can see the second dark spot. So that second dark spot went away. More of them appeared. So the main dark spot lasted for several years, but these secondary spots were transient phenomena. So yeah, we saw the dark spot originate in 2018. And then with the OPAL data, we saw it dissipate in 2022. And so for the first time, we were able to constrain the full lifetime of a dark spot on Neptune. And all the previous observations, so this last one, we call it NDS 2018, Northern Dark Spot discovered in 2018. And this is the first one where we saw the origin, we watched it evolve, and we saw it dissipate over time. All the previous ones, either we missed the origin or we missed the dissipation, or both. So this is the first time we have a full timeline of a dark spot. And we did a similar search for Uranus, and we found that in comparison, Uranus dark spots are much rarer. This was, well, in the upper left here, we see a dark spot that was detected on Uranus in this paper by Heidi Hamel, and this was seen in a combination of Hubble and ground-based adaptive optics imaging of the planet. But so for this dark spot in the early 2000s, we were able to figure out what is the best filter to look at it. And in this case, it's in kind of green wavelengths, 550-ish nanometers. And based on that observation, we did a search of Uranus in the OPAL data, subtracted off the mean brightness so that we could get down to the noise level, and we did not see any dark spots of the same contrast as before, and definitely nothing of the strong contrast that we saw on Neptune. So although this summer project led by Russell Mappier was not successful in detecting a dark spot, it was a really thorough investigation and allowed us to do a comparison. We call it comparative planetology between Uranus and Neptune. Vortices on Jupiter, of course, we're familiar with the Great Red Spot, which in this ultraviolet false color image appears very dark. It absorbs in the ultraviolet, it absorbs at blue wavelengths, and that's why it's called the red spot. But we discovered some other dark vortices in the polar regions. And in the polar regions, there's sort of this uniform, mostly uniform, dark stratospheric haze. And if you look at the planet in a polar projection, in this haze composite image, you can see that that haze is centered around the pole. But we are able to see some isolated dark spots within this haze by subtracting off the mean brightness. So when you do that, you get these maps of the polar region, and you can see at sometimes there are these concentrated dark spots in the polar haze, and sometimes there are not. And so this study led by undergraduate student Troy Tsubota used OPAL data as well as data from a few other programs that were able to produce global maps of the polar regions and the ultraviolet wavelengths. So in these maps, you can see the region where the aurora usually appear. It's shown as a kind of a cyan oval in the upper left there. And then most of the times when these dark spots appear, those dark spots are falling inside the auroral oval. There is one exception. In 2015, you can see it's way outside, and that was something that we saw with Cassini, where it captured a movie of this dark spot, which is transient, and it drifted outside the auroral oval and dissipated. But based on this study, we found out that it's actually a lot more common in the south than the north. The one that Cassini saw was in the north. And we came up with an explanation that is really interesting to me because it follows this theme that we're finding in a lot of planetary science, which is that there's all these different layers of planets that are interconnected. So Jupiter has a very strong magnetic field. That's generated in the interior of the planet where there's liquid metallic hydrogen. A dynamo activity creates a strong offset dipole field, and the magnetic field lines extend way out into the magnetosphere of the planet, where there is plasma produced by Io and other satellites. That plasma exerts a drag on the magnetic field lines, so they don't fully co-rotate with the planet. It's in sub-co-rotation. So those field lines, which are connected into the ionosphere, as they're dragged by this magnetospheric plasma effect, they're spinning the atmosphere in the ionosphere the wrong way. They're slowing it down up there. And so that's in the ionosphere where ions can sense this magnetic field. But then that is connected deeper down into the neutral atmosphere. And we compared observations from other studies showing that as you get lower down into the atmosphere, the strength of that spinning is going down. So it's sort of like you're looking at the tip of a tornado here. And as that tornado touches down into the stratospheric aerosols, it's stirring them up and creating this localized dark spot sometimes. Um, so yeah, so going back to this more famous dark spot, the Great Red Spot, we developed a code long before OPAL to kind of measure the velocities in this vortex with a very high fidelity. And so we take a time series of imaging data with Hubble and measure the velocity field. You can then use that velocity field to kind of morph the clouds in a physically realistic way. And so this animation shows you what would happen if you could somehow view the Great Red Spot over a period of 10 hours. So Jupiter is rotating over 10 hours. And so as a Great Red Spot hits the day side, we take our pictures with Hubble, we measure the velocity field, and then we reconstruct what would have happened. This particular view is absolutely impossible because the Great Red Spot is going into the night side. So then you're not going to see what it looks like in the night side. But we're able to reconstruct how that flow would have persisted over a 10-hour period based on our Hubble observations. And so we did this for every year of the OPAL data in a 2021 paper. And compared with other observations, this is comparing with observations from Voyager, from Galileo, and we were able to show that the Great Red Spot is gradually shrinking in size. This is clearly seen even just from visual observations. The Pioneer Jupiter image is shown here, and the Great Red Spot is so much larger and so much more elongated. I don't think you have to be a Jupiter expert to see that Pioneer and then James Webb here in this 2022 image are showing the Great Red Spot in very different states. It has shrunk and it has gotten more circular. But the graph is actually showing something different than you can see with your eyes. We're measuring the size of it based on the velocity field itself. And so that's kind of a new measurement. Let me skip ahead 2 slides here, just to show that as it was shrinking, we were able to show that the wind speed is slightly increasing. And this is not increasing by very much. It's maybe by 10 meters per second over time. But this is something that we could only do because of the very high precision that we get from Hubble Space Telescope's high resolution imaging. So I mentioned Hubble tying in with observations from previous spacecraft like Voyager. A really interesting study came out last year led by Agustin Sanchez La Vega, showing the Great Red Spot shrinking over time in this timeline. There was a period when there were no giant spots on Jupiter. And then back in the 1600s and 1700s, there was another large spot in the southern hemisphere. So this other spot, based on these plots, it looks like these large vortices on Jupiter shrink over time. And so I'm pretty convinced that the permanent spot that was seen in the 1600s and 1700s, including by the astronomer Cassini, who was observing at that time, is a different spot than the one that we now know as the Great Red Spot. In the 1600s and 1700s, there were some professional scientific journal reports, but back in the time when they described this spot, they didn't say what color it was. So Agustin Sanchez La Vega went to the museum and found a painting from that time period showing Jupiter. And if you zoom in, you can see that there's a spot on the planet in the planet's atmosphere. And that spot has a reddish dark color. So even though the journal articles didn't mention the color of the spot, this really unique kind of archival research showed that, at least in the painter's mind, that spot was red. Now, we don't know whether the artist had consulted with astronomers and found out what color to paint it, but it's possible that it was also a red spot. Again, with this comparative planetology, the red spot, probably the closest analog to the red spot on Earth is not an atmospheric storm, but these vortices that are present in the ocean. These eddies in the ocean, they call them salt lenses because they're spinning, and they're pancake vortices. So in this plot in the upper left, they look more like a pill shape. But if you were to look at the scale, this is degrees of latitude here, and this is meters on the y-axis. So these vortices are much wider than they are tall, and they're also distinguished by compositional variability, salinity, and the stratified ocean is considered to be similar to the stratified atmosphere of Jupiter, in which the great red spot's embedded. So we looked to a study of a ocean eddy, which showed that as it shrank over time, the speeds increased slightly within the velocities increased slightly within that ocean eddy. And so that is the potential explanation for what we saw with the great red spot. As it's shrinking over the opal time period, its winds are also increasing. So again, we compared James Webb and Hubble data that showed a narrow high-speed jet at the equator, but it also showed wind shear within the great red spot. So James Webb can see higher up in the atmosphere when there's enough haze and high altitude particles, and the equatorial region and the great red spot are two of the regions where we really do have this high altitude haze that helps us measure things. So there's a few more topics that I'm gonna go through a little more quickly here. OPAL has also been used to study different types of waves. So in the upper left here, you see some really fine scale wave packets in the North Equatorial Belt. And we were able to kind of link those with vortexes that were seen nearby. And then Hubble also saw in the ultraviolet filter periodic brightness variation that is very similar to something that was reported in the infrared from ground-based data. And these are in the same time period, 2017. So Hubble is showing a common phenomenon at a wavelength that we cannot see from the ground. This is a near ultraviolet wavelength. Waves are also seen on the ice giants. So here in Neptune, you can see on the left here, cylindrical map, and this stripe at the bottom of the map, you can see it's a little bit wavy. This has one wavelength around the planet, so it's a n equals 1 wave. And this is something that has been seen since Voyager. If you look at the polar projection, it looks like a circle, but it's offset. So it's closer to the pole on one side and farther from the pole on the other side. So we're able to study this over a longer time period using the OPAL data. For Saturn, we are trying to understand the colors of the clouds in Saturn, and the OPAL data. This is an early report based on the first 3 years of OPAL data, showing that there are some changes in the cloud color, and it's a lot more complicated than Jupiter. If we use all of the OPAL filters, we can see that some of these bands in Saturn's atmosphere change color in one filter, but not another one. And so we used a technique called principal components analysis to really figure out what are the main types of variation in the broadband spectrum of Saturn as seen by the OPAL program. For Uranus, OPAL has contributed to a study of seasonal change in the polar cap. You can see in this sequence of images, A, B, C, D, E, F. This is in the infrared, a time series including Hubble and ground-based data showing that as Uranus rotates, it has sort of a bright polar region in the infrared. And then as the pole rotates out of view and you see Uranus in the solstice configuration, the poles have faded in brightness. And then as the seasons continue to change, the opposite pole begins to brighten. And this change in the brightness has been associated with a combination of changes in the haze particles as well as the methane abundance using combined data from ground-based and Hubble observations. Again, the OPAL data have contributed to observations of the cloud structure on Uranus and Neptune, and the study led by Pat Irwin pointed out something somewhat surprising. So in the past, we think of these cloud layers and the giant planets as different ices depending on what temperature the atmosphere is. But this study really indicated that all of these cloud layers have a lot of haze, which we think is photochemically produced at high altitudes and then kind of drifts down and mixes with the clouds and contributes to their physics and their composition. So there's a lot of, again, mixing between layers, a theme that keeps coming up in current planetary science. So I will leave you with my conclusion slide. I don't know if there's any questions, but start typing them in if you have thought of any. And I'll just review that what OPAL does is it provides consistent imaging on an annual cadence, and it delivers this data to the public right away, and also provides process data that make it easier to immediately start doing science without having to duplicate some of the analysis that we do. And this really enables research on time variable phenomenon, and that's one of the most important areas of planetary research. So the science results of OPAL range across convection, moist convective storms, to zonal jets and their interaction with convective storms, cycles of aerosol variability, seasonal and other cycles, non-seasonal cycles, and a lot of different studies of vortices on the giant planets, their evolution, their life cycles, the vertical and horizontal interactions with the environment. And by studying these vortices, it also helps us understand what are the deeper properties of the atmosphere. And also with OPAL, we have studied waves and turbulence and use these as probes of the structure of the atmosphere. OPAL data provides context for a wide range of data sets from spacecraft to the ground, also comparison with theoretical investigation simulations. And it's been used for a large number of early career research projects. And OPAL really helps us to extend the timeline of studies that have happened before, and hopefully future studies as well. Some of our next steps include more data products delivered, not just the cylindrical maps, continued science research, of course, and hopefully OPAL can serve as a model for future long-term studies using other facilities, either from space telescopes or ground-based telescopes. So thank you for listening.
Thank you very much, Mike, for the very interesting and inspiring talk. I mean, it's amazing to see how, not only the Hubble Space Telescope produce amazing results on these objects, but the importance of having a consistent monitoring of these systems. And so I think the beauty of this program is this coverage over time and the beautiful results that you've been able to achieve. So congratulations to you, Amy, Simon, and the team for bringing this. So is OPAL, I have a question on my own, is OPAL still continuing or
Oh,
it has
yes.
fin
Yeah, it's continuing. I mean, the science goals are maintained. One of the things we want to study is seasonal change. So Neptune's orbit is I forget what. I mean, this is the kind of thing you look up on Wikipedia, but it's less than 200 years and more than 150 years, anyways. So I don't think Hubble is going to last that long, but we want to get as much data as we can. And in fact, we just got data on Saturn most recently with OPAL. So those data are being processed. There's some interesting things happening on Saturn that the amateur astronomers have noticed a new decagon wave, like a 10-sided wave in the atmosphere. And so OPAL data are going to provide a high resolution look at that phenomena.
Fantastic. Well, we have a number of questions to answer, so I will start reading. So the first question was from William Wall, and it is on the topic of weather forecasts. So William is asking, have you and your team become adept at weather forecasts for the outer planets? And also continuing related to the weather forecast question, can you take past images of an outer planet and predict future images of that planet?
That, as far as I know, that has not been attempted. You mean something like training an AI model on the time series of images and having it extrapolate? Yeah, I don't think that has been done. Can we predict the weather? There are some things that we've really noticed a cyclical behavior, such as that storm in Jupiter's atmosphere, the superstorm. Um, this seems to happen every approximately 5 years. And so if we watch that speed of the jet that the storm is associated with increase over time, we can really see when, okay, it's really sped up. I think there's going to be an outbreak soon. So that is one area where we probably can predict it a little bit. But in other regions, there's a lot of surprises that we're continuing to find with these planets. I think with Uranus, we have watched this transition from one pole being bright to no poles being bright to the other pole being bright. So I think we would expect that to happen seasonally on Uranus. But there are other changes that we see on the planets, like the narrowing of the equatorial belt um, that gave us the stealth superstorm situation. That has never really been seen before. So there are a lot of new things to discover if we keep looking long enough.
Thank you. So we have a question from Steven Spangler. For convection on Earth, solar heating on the ground creates a temperature gradient, which is unstable to convection. What is the heating source at the base of the convective layer on Jupiter and Saturn?
Okay, so ultimately it is gravitational contraction. So yeah, there is some solar heating to these planets, but one of the things that Voyager and then later spacecraft demonstrated is that the sun is shining on the planets. They're reflecting some of the sunlight away. They're absorbing some of that heat, and then they're radiating heat, but they're radiating more than they're absorbing from the sun. So there is an internal source of heat that we don't have on the Earth that is gravitational settling. As the planet ages over time, it's kind of shrinking, and the interior is heating up. And some of that shrinking involves processes like helium rain on Jupiter and Saturn. So you have this interior mix of helium and hydrogen, but at certain pressures and temperatures, the helium will rain out, and that gravitational settling generates a type of heat that will then eventually come out of the planet. So they are heated from below like the Earth, but the source of that heat is internal, unlike the Earth. So that's one difference. And then the other difference with moist convection, particularly on the Earth, we have a nitrogen atmosphere and we have H2O. Nitrogen has a molecular weight of 28, H2O has a molecular weight of 18. So moist air is actually lighter. If you get some moist air, it's the same temperature as some dry air, it's going to want to rise. And then as it cools off, you can have condensation, release of latent heat, and moist convection on the Earth. On the giant planets, they're mainly a hydrogen atmosphere, so their dry air is very light. Their moist air is very heavy. So moist air doesn't want to rise. You have to actually heat it. And then once it does rise, it can store a lot of energy that gets released. So these convective storms are very energetic just from condensing out the water and other cloud materials. So that's another difference between the planets.
Thank you. So we have a question from Namra Habib. Going back to the episodic storms, do theoretical studies match the period of observed convective storms from the OPAL data? How constrained is the theory?
Right. That is an open area of research. So if I go back to the animation, well, let's just look at this frame from that or time series from that animation. This simulation from Sugiyama et al.'s team had episodic convection, and they used different conditions in order to speed up their model and have it be, something that you could uh, get results in a fast enough period of time. So they used more intense heating, and they found a certain periodicity that was affected by how much water you have in the atmosphere. So in later papers, they did studies with less water or more water, and they found out if you have less water, then it's just continually convecting. If you have more water, then convection is suppressed until the heat builds up, and then you have a storm. If you have even more water, it takes a long time before the storm can erupt. So there's that dependence. Now, on Jupiter, the superstorms we're seeing, those are maybe every 5 years or so, but there was a period where there were no storms, and that's only at one latitude. So at other latitudes, the storms are kind of continually erupting. Um, so these simulations with the episodic convection, they make a prediction of how often you should have convection, but the simulations are either one-dimensional simulations or two-dimensional simulations, and the planets are three-dimensional. So this is an area where we're doing a lot of research in more complicated 3D simulations to try and figure out what is the effect of water on the convective process and whether we can see these same periodicities in a more realistic model.
Thank you. We have another question from Hugh Hudson. Are there time series of seismic standing waves in the outer planets?
Yes, I should have included a slide on that. So this is a very new area of research. So seismic waves on the outer planets. This is very different than, I don't know if you heard, but there was an earthquake in Berkeley a couple days ago. I mean, it wasn't that big, but it woke me up at 3 in the morning. Um, Seismic waves on the Earth are waves that are propagating along the solid crust and propagating through the planet. And some of them can pass through the liquid part of the planet. In the case of the giant planets, there is no solid surface, so the waves are different, and they're more of oscillations from interior processes. So it's more like the giant planets are resonating, and like kind of like a bell. When a bell resonates, it has specific tones that it'll resonate at, other tones that it won't. So if you can measure how the planet is pulsating, then yeah, you can find out about the interior structure. And this is something that has been done for Jupiter. And eventually we want to do this for all the giant planets, but It's a specific type of observation. It's Doppler imaging, where you look at the planet and you can see different parts of the planet moving towards or away from us. And it's very difficult to do for a number of technical reasons. But the first real exciting application of this technique was published, I think, this year or last year. And they used OPAL data to compare with it, because as you're measuring those pulsations, you're also measuring winds. They have to subtract those winds off. And they compared the winds with what OPAL is finding as kind of a validation that their measurements are correct.
Thank you. One more question from Boris Galperin. We found zonostrophic turbulence regime on Jupiter and Saturn. There might be enough information today to find out if this regime develops also on Uranus and Neptune. This can be seen in the zonal and residual spectra.
Yeah, so that is super challenging for Uranus and Neptune. And Boris Galperin is a world-renowned expert in zonal flows on the giant planets, so I'm a little intimidated by the question. But for Uranus and Neptune, where are the zonal winds of these planets? Uranus and Neptune, you can see these little points here. Let's see, 1986 is Voyager. And that is a smooth profile. Voyager, like these ground-based observations that you see in blue and red, had a lot of scatter. So it's hard for us to measure the zonal winds. And one of the reasons is the cloud traces are rare. They're these discrete clouds. We can't tell really what altitude they're at. There's vertical wind shear. And so in order to really find the zonal residuals, as Boris was saying, you have to subtract off the background flow, but we don't particularly know what the background flow is. It's hard to tell the difference in this scatter. Are we seeing temporal variation? Are we seeing wave activity that you want to measure for this turbulence? Are we seeing vertical wind shear? So there's a combination of effects here. I think an orbiter mission to these planets would be a really good way to get better high fidelity wind measurements and perhaps do this study.
Thank you, Mike. One last question. We're getting to the top of the hour. Shaktivel Pillai, has OPAL data observed any variation in the Jupiter magnetic field strength over space and time? Can you shed some light on what mechanisms drive this variation?
Variation up. Can you repeat which planet the question was about?
So Jupiter's magnetic field strength.
Jupiter's magnetic field strength is pretty constant. Some of the big questions these days are whether Uranus and Neptune have more rapidly varying fields, because their magnetic fields were mapped by Voyager, and we don't really have any other spacecraft observations of those planets. Now, with the OPAL program, we're really just looking at reflected sunlight. Even our UV observations are in the near UV, where it's solar ultraviolet reflecting off of the clouds and coming back to us. So we are not seeing auroral emissions, which can show us kind of the position of magnetic field line interactions with the atmosphere. We're not directly sensitive to that with OPAL. So with Hubble, you want to look in the ultraviolet to see that, the deeper ultraviolet to see that type of activity. But with Uranus and Neptune, the ultraviolet aurorae haven't been seen very reliably on those planets. James Webb has made huge advances in our understanding of the auroras on Uranus and Neptune because H3+ emission is really, really clear in the infrared spectrum. So look for some new results on those planets in the coming years.